All right, this is the last example problem video from the very long Taylor and Maclaurin series section. And what we're going to do in this video is we'll be given a power series like this, and we want to find what the infinite sum is. So not a partial sum, but the actual infinite sum. So how are we going to do that? Well, the idea is all we're going to do is we'll look at something like this, and then we'll compare it to the table of Maclaurin series that we have, and use this table to identify what function the series corresponds to. And that function, either the function itself, or maybe if we're given a series where there's no x in it, there's a value been put in place for the x, that will be the actual infinite series, right? The value of this infinite series here is cosine x. So if they put in x is equal to pi over 4, for example, well, then the sum of this infinite series is cosine of pi over 4. Okay, so which one of these Maclaurin series, we can see this is a Maclaurin series, it's centered at 0, it's not x minus something to the 4n. Which of these Maclaurin series does this correspond to? Well, it looks similar to the cosine of x, minus 1 to the n, and then maybe you input x squared for x, so you have x to the 4n, but then there's this 2n factorial down here, which is not, that's not a match, but potentially it could be something related to cosine x. Now we see e to the x here. This has the n factorial in the denominator, and you could say e to the x to the 4th power and get x to the 4n over n factorial, but then there's this minus 1 to the n out front. Okay, so if you think about it though, so e to the x is okay, we can get this minus 1 to the n doing this, by putting a minus sign. So what you get is minus x to the 4th to the n. Okay. Now you can take out that minus 1 to the n, and what are you left with? X to the 4n over n factorial. And there you go. So this infinite series here is equal to e to the minus x to the 4 power. Okay, what do we have here? So you can see that from the previous problem, we don't really have to worry about an alternating term. We can create that if we need. So let's just focus on the non-alternating portion. So we've got just this n in the denominator, and I look and see natural log of 1 plus x is the only one of these Maclaurin series with just an n in the denominator. But also notice there's no x here. So that means something was input for the x. And so in that case, clearly we're dealing with natural log of 1 plus x, because we can write this as you see, so we've got this with x is equal to 3/5, which is within the radius of convergence. You can input any x between plus and minus 1. So this is equal to natural log of 1 plus 3/5. And we can actually simplify this. So 1 is 5 over 5 plus 3/5 is 8/5. So natural log of 8/5, and if we want to go a step further, we could say natural log of 8 minus natural log of 5, and we could keep going if we wanted to, just to show you. This is natural log of 2 cubed minus natural log of 5. This is 3 natural log of 2 minus natural log of 5. Okay, so, okay, 2n plus 1 factorial, see that here. We got a minus 1 to the n. So yeah, I can see exactly what this is. This is, so let me move this. Okay, you see we can write this as minus 1 to the n, and then pi over 4 to the 2n plus 1. You see? So this is sine of pi over 4. Which is root 2 over 2. This infinite series here is equal to root 2 over 2. Okay, so here, what is this series? Let's bring this off over here. So, okay, this is equal to what? So, okay, we've got in the denominator 1 factorial, 2 factorial, 3 factorial, 4 factorial. So, an n factorial, there's no alternating term. Okay, and then looks like 3 to the n. So, wait, let's look here. Okay, so yeah, I mean, this is 3 to the n up here, but this starts at 1. Okay, so we can see that this is e to the x with x equal to 3. However, we're starting at not at 0, but at 1. Okay, so the issue with that is we can't just say this is e cubed. Can't just say that. So what do we do? Well, what we're going to do is, so e cubed is equal to this. Okay, now let's write this out, the like, you know, in an expanded form like this. So when n is equal to 0, we've got 1. When n is equal to 1, we've got 3. N is equal to 2. Okay, so how do these two compare? Well, this is exactly equal to this, but just subtracting out 1. So all we got to do is minus 1. Okay, what do we have here? Okay, we see we have this 2n factorial into the denominator, minus 1 to the n. So yeah, we can see what this is. This is just cosine of x with x equal to pi over 6. Because we can write this as so cosine pi over 6 root 3 over 2. Okay, we've got an n factorial in the denominator. Here's n factorial, and this is going to, we can write the 3 to the n over 5 to the n as 3/5 to the n. So we can see that this is e to the 3/5. Okay, what do we have here? Let's write this as a summation. Okay, so it looks like we can start at 0 and we can say natural log of 2 to the n over n factorial. 0 factorial is 1. 1 factorial is 1. Oh, but then we need an alternating term. So minus 1 to the n, natural log of 2 to the n over n factorial. So there you go. There's the summation. Now we've got, let's see, n factorial. So, okay, this would be, we've got the minus 1 to the n, but if we say e to the minus natural log of 2, so you put in minus natural log of 2 for x, that brings out a minus 1 to the n, then you're left with natural log of 2 to the n over n factorial. So this is e to the minus natural log of 2. Okay, now we can simplify this. So this is e, we could bring the minus 1 as an exponent on the 2, so we've got e to the natural log of 1/2. Now e to the natural log of anything is just what's the argument here, so this is 1/2. Okay, what do we have here? This is, so the sum going to infinity. So it looks like we've got a, if we're starting at 0, then we've got a 2 to the 2n plus 1, and then times 2n plus 1. And then there's also, it's also alternating, so it's going to be minus 1 to the n. Okay, so here's a 2n plus 1 in the denominator with no factorial, and then x to the 2n plus 1. So yeah, we can, we're dealing with inverse tangent of x. We can rewrite this as so minus 1 to the n, and then we can write the 2 to the 2n plus 1 in the denominator as 1/2 to the 2n plus 1 over 2n plus 1. And that we can see matches this here with x equal to 1/2. So this is, let's see if that comes out to anything finite, or like, you know, if there's a more exact answer than this. No, so that's it.